Hello, welcome. See, we are going to see in this video some more ideas about connectedness on topological spaces. Here we first we define the concept of component. A component of a topological space is a connected subset of X. Here, suppose X be the topological space. Then we can say that it's a connected subset of the topological space, which is not a proper subset of any other connected subset of X. See, we want to repeat it. So a component of a topological space. Component of a topological space is a connected subset of. First of all, it must be connected. First of all, it must be connected, a connected subset of X. But in addition to that, it must satisfy the condition that it cannot be a proper subset. It should not be a proper subset of any other connected subset of the same topological space. So which is not a proper subset of any connected subset of X. We have some properties of connected of the components to discuss now. So see the properties of the components. The property 1. So each point A in X belongs to exactly one component. See, we have the topological space X, and then each point of X, each point A of X must belong to exactly one component. That means if A is a point of the topological space, then A cannot be a member of two different components of the topological space. How can we prove this? See, suppose that A is, and we choose an element, a point of X, A be an element of X. Suppose also it belongs to two different components, say C1 and C2 of the same space X. So we choose a point, let A be a point of X, and that is contained in the two different components C1 and C2. Then C1 and C2, since they are components, they are connected. C1 and C2 are connected separately, they are connected. But now we know that A is a common point which is shared by C1 and C2. So A is common to C1 and C2. Thus, by using the theorem, some previous theorem on connectedness, on union of two connected subspaces of a topological space which shares some common point, and we know that their union will also be connected. Thus, C1 union C2 is connected, and also C1 contains C1 is contained in C1 union C2, and C2 is also contained in C1 union C2. Actually, this situation contradicts the maximality of the components C1 and C2. Since C1 and C2 are components, they are of their maximal size. See, that means that cannot be contained in a bigger component. See, C1 and C2 cannot be contained in a bigger component of the topological space. But what we have obtained now, that says that C1 can be contained in a bigger part, in a bigger connected part. That is, C1 is a member of C1 is contained in C1 union C2, and also C2 is contained in C1 union C2. But that's actually a contradiction. Contradiction to what? It contradicts the maximality of the component. See, since C1 and C2 are components, they are of maximum size. See, that cannot be contained in it cannot be properly contained in some other component. Okay, so now see, that can again be that can be more. It can be, this concept can be explained more. See, that is the idea. This idea, that idea I have completed, but it can be further explained. So if we get that, thus we get that C1 is a subset of C1 union C2. So since C1 union C2 is a component, it's connected. So thus we get that C1 is a subset of C1 union C2, and C2 is also a subset of C1 union C2. If C1 and C2 are different, we know that C1 and C2 are different. That means C1 contains some point which are not in C2, and C2 contains some points which are not in C1, since C1 and C2 are two different components. Okay, so C1 and C2 are proper subsets of C1 union C2. Therefore C1 union C2 is a connected subset of X, and that contains C1 as a proper subset. So it contradicts the maximality of C1 and C2. So that's all. That's the end of the proof of this this result. Okay, so A must belong to exactly, so we have to correct it, correct our assumption that A belongs to two different components, and that's actually wrong. So we have to correct it that A can be a member of exactly one component in the topological space X. The property 2. The component CA containing A is the union of all connected subsets of X which contains A, and thus it is the largest connected subset of X which contains A. See, the component CA, we name the component the connected part of the topological space X which contains a point A, where A is a member of X, A is an element of X, and CA is the component that contains the point A. It is the union of all connected subsets of X which contains A, and thus it is the largest connected subset of X which contains A. So component of the space X which contains A is the largest connected subset of X which contains that point A. To prove this, let us consider the collection of subsets of X. Let AI, the set, let us consider the set AI where AI is subset of X such that A is an element of AI, where small a is an element of AI, be the collection of all subsets of X which contains A, and also they are connected. In addition to that, we have to write that each AI is connected. So here we consider only those connected subsets of X which contains A. Actually by mistake it was not it's not written there. So here we consider only those subsets of X which contains A, and connected subsets of X which contains A. Then we define C is equal to, let's now define C equal to union of AI where I is an element of I. Then C, we define C equal to a new set. We can define union of AI where I is an element of I, because because of the fact that each AI contains the point A, so A is common to each and every member of this family, and thus their intersection of AI where I varies in the index set is non-empty, and that set, the intersection contains at least one element A, small a. And therefore, using the theorem that we have previously proved, we can show that C, if C is defined as union of AI where I is an element of I, that set C is connected. And also C is a component, and also you can show that now C is a component. So this defined set C is connected, and also we can show that C is a component. In order to show that C is a component, what we want to do, we want to show that there does not exist a bigger subset of X which properly contains C, which is connected also. So there does not exist. Then we want to show that there does not exist a connected subset of X which properly contains C. So suppose that C is not a component. So for the time being, we assume that C is not a component. Then C is contained in a bigger connected set, say C prime. Clearly, A is an element of C, A is a member of C, and C is a subset of C prime. And see here C prime is connected, C is also connected. But A is a member of C prime. As A is a member of C prime, the C prime must be a member of this family, right? Because here we are considering those connected subsets of X which contain the point A. Only those members we are considering here. to include in this family. So C prime must be present there, and since C prime is present there, when we take the union, and this that member C prime must be present there on the right side in this union. As a result, C prime is a subset of C. So whenever there exists a bigger connected set which properly contains C and also contains A, then we get that that new bigger set is a subset of C. So that means C equal to C prime. Oh, okay, and thus we get that C equal to C prime, and therefore we get that C is maximal. That this implies that C is of a bigger size, or C has the biggest size, which contains A, and also it is connected, and thus we get that C is a component. The third property. The statement of the third property is that for points A and B in X, for 2 points A and B in X, the component CA and CB, we index the component which contains A by CA and index the component which contains B by CB, are either identical or they are disjoint. See, CA and CB are the components, they are containing A and B respectively, and they are either identical or they are disjoint. Identical means they are equal, and otherwise if either they are equal or they are completely disjoint. So if to prove this, if CA and CB are disjoint, we suppose that CA and CB are disjoint, then there is nothing to prove. So if they are disjoint, first of all we suppose CA and CB are disjoint, then there is nothing to prove. So as the remaining case, we have two cases. In the first case, we think that CA and CB are disjoint. We are done then. But in the second case, we suppose that they are not disjoint. That means CA and CB have some point in common, right? Okay, and then they share some point. That point you can take one of such point as X. See, X be that point which is common to CA and CB. So let us choose X, an element of CA intersection CB. Then CA union CB will be connected. It's because CA and CB are components. They are connected. They are separately connected. Itself they are connected, and also since X is a point which is common to CA and CB, we get that their union must be connected. Using the previous suitable previous result, we get that CA union CB is connected. But CA and CA union CB, as it is connected, and that must be bigger than CA, and also it must be bigger than CB. But that actually contradicts the maximality of CA and CB, as CA and CB are components. So this is a contradiction actually, and this situation can be overcome only by correcting the statement that there exists some point which is common to CA and CB. So in the second case, we have assumed that there exists some point which is common to CA and CB, and that is the reason finally we got that contradiction. So we have to correct that statement, and it must be corrected like there does not exist any point which is common to CA and CB. That means CA and CB are completely disjoint. Next property, so we have that the property 4. In the property 4, we have the statement every connected subset of X is contained in a component. See, every connected subset of X is contained in a component. Wait, how can we show this? How can we prove this? We consider every connected subset. So we are taking connected subset of X, and that will be contained in a component. So for that, let A be a connected subset of X. We choose a subset of X that is A and name it A, and that is connected. And let small a be an element of A. Let us choose small a point in A. Small a be an element of A. And we consider CA is the component of X which contains A. And CA is connected, and also it is the biggest connected subset of X that can contain A. As a result, by the definition of the component which contains A, it is clear that since X is connected, then X must be a subset of CA. Okay, then by the definition of CA, and also since A is connected, and thus we get that A is a subset of CA. So A is contained in that component. Yeah, that's the end of thus we can complete that proof for the property 4. Next, the property 5, that has the statement each component of X is a closed set. Each component of a topological space X is a closed set. To prove this, let's choose a component. Let C be a component of X. It's arbitrarily chosen. C be an arbitrary component of X. First, we shall show that the closure of C here can be written as C closure, C bar, C closure is also connected. So for that, in order to prove that C is closed, C is a closed set, we want to show that closure of C is also connected. We shall prove a more general case. See, in order to show that the closure of C is also connected, we want to prove, or we shall prove, a more general case. So if E is a connected subset of a topological space, see, if E is a connected subset of a topological space, then closure of E, that is the closure of the set E, is also a connected subset of X. To prove this, suppose that the closure of E is not closed. Then there exists two okay, it is not closed, it is not connected actually. So suppose closure of A is not closed, not connected, and this is a mistake, it must be corrected. See, to prove this, what we want to do, we want to show that closure of E is also a connected subset of X. So in order to show that, we just think about the opposite situation, that is closure of E is not connected. So okay, please correct it as connected. So closure of A is not connected. Then there exists two subsets, open subsets A and B, which makes a disconnection for closure of E. That's closure of A equal to A union B. And closure A intersection B equal to null set equal to A intersection closure of B. And A and B are non-empty sets. Okay, A and B are also non-empty. They are non-empty set also. Okay, and these are the conditions for the existence of a disconnection. Since we assume that, since we suppose that a closure of E is disconnected, and we can choose two sets having these properties. Since E is connected, but we know that E is connected. It is given that E is connected. In the beginning, we have chosen E as a connected subset. So since E is connected, A and B do not make a separation of E. Okay. Yeah, it's clear. Since E is connected, A and B cannot make a separation for E. Suppose A and B make a separation for E, what happens? Then E will be disconnected. That contradicts the accepted statement, which is accepted. That it actually then contradicts the statement which is accepted as true. Okay, and so A and B cannot make a separation for E, and so E is not equal to A union B. So we have to accept that E is not equal to A union B, and therefore there exists some point P, an element of closure E minus E. There exists some point P in closure of E minus E, and let E double prime, we define E double prime equal to set P, such that P is an element of E prime. But what is E prime? E prime is the set of all derived set of all limit points of E. We know that E prime is normally it is used to denote the set of all limit points of E. So let P be a limit point. Let P be a limit point of the set E, and P and such P points are chosen. we are choosing those limit points of E are taken, and but all those limit points are not there, not a member of this set. In addition to that, that point, limit point, must satisfy the condition that it is not actually present in E. So E double prime is the set of those limit points of limit points of E, those limit points of E which are not a member of E, but not a member of E. Only those limit points are taken here and named as E double prime, and P is clearly a limit point of E. Then P is a limit point of E. It's okay, but P is not a member of E. Since E is connected, and we can see that either E is a subset of A. See, yes, since E is connected, then either E is a subset of A or E is a subset of B. Let us take the situation that E is a subset of A. Yeah, it's convenient to take that either A is a subset of A or E is a subset of B. So let us take E is a subset of A. Since B is not equal to the empty set, since B is not equal to the empty set, then B intersection E double prime, B intersection E double prime will not be an empty set. Since B is not an empty set, B is not an empty set, so B intersection E double prime is also not an empty set, and therefore closure of E is a subset of thus we know that closure of A is a subset of closure of E is a subset of closure of A. Thus closure of E is a subset of closure of A. But why? Because we have chosen that E is a subset of A. Since E is a subset of A, it is clear that none of the all limit points of E must be a limit point of A, and it cannot be a limit point of B. That is the thing. So since E is a subset of A clearly, and A and B are making a separation for the set closure of E, all the limit points of E must be a limit point of A, and thus closure of E must be a subset of closure of A, and therefore E double prime is a subset of and also E double prime is a subset of closure of E. See, E double prime is a subset of closure of E, and therefore some element of E double prime are in B. This means that some elements of E double prime are in B, and all elements of E double prime are in closure of A. See, the some elements of E double prime are in B, and all elements of E double prime are in closure of A, and therefore closure of A intersection B is non-empty. Thus we get that, finally we get that closure of A intersection B is non-empty, and this is actually a contradiction. This contradicts the fact that closure A intersection B is empty. Okay, therefore we have to conclude that closure of A is also connected. We have to correct the assumption that closure of A is disconnected. Earlier we have chosen the assumption that we have used the assumption that closure of E is disconnected, and then based on that assumption only we proceeded to obtain this contradiction, and that closure of A intersection B is not empty. And got the contradiction that contradiction to the statement that closure of A intersection B equal to empty, equal to an empty set. Okay, thus in particular, so this is the general situation, and in particular then we can take here what is the relevance of this proof here in our problem, in the current situation, and we can make it clear. In particular, we can take E equal to A. Here we can take E equal to a component of X. So we can take E as a component of X, and then closure of the component is also connected. Then the closure of that component, see, at the place of E we can take a component of X, and then the closure of that component it's also connected, and therefore closure of C is connected, and hence we get that C is a subset of Thus we get that C is a subset of a closure of C, and this is possible only if C equal to C closure C. Thus we get that C is a subset of a closure of C, and we know that closure of C is a bigger it's little bigger than C. And normally, closure of C can contain some more points of C. Otherwise it must be equal to C. But in the current situation, since closure of C is closure of C is also a is connected, and is a subset of closure of C, and this is possible only if C equal to closure of C, and so C is closed. And thus we are now at the end of the proof of the result. Okay, thank you.